Hello. Now that we're done with translational mechanical system, we also want to look at the rotational mechanical system. So they are somewhat similar. The only differs in the direction of the motion. If for translational, this is the linear motion. While for a rotational, we have rotational motion. It rotates. So first, let us define different parameters for rotational mechanical system. So if in translational we have displacement. Here in rotational we have what we call also the displacement. This is angular displacement. Angular displacement theta. For the velocity, we have here omega. This is not natural frequency. This is omega angular velocity. Angular velocity. Then alpha for the angular acceleration. Then if you want to solve for omega, this is just equal to the first derivative of angular displacement, while alpha or the angular frequency is just equal to the second derivative of the angular displacement. So these are the different parameters. Then we look at also if we have just like in translational system, if we apply instead of force now, the equivalent of force now here is we call it this one tau. This is torque. So it's now torque instead of force, but they mean the same thing, but only in a different uh, motion. And also for mass, instead of m, we use the inertia, rotational inertia, g. We denote it as g. So these are the things that we will be modeling. So we still have a spring in rotational. So if we have cylinder tube or anything, you want to rotate that. If it's so long, then the if this is that cylinder or anything, if you rotate this in that direction, this part at the end part will not rotate directly. It will twist, and that twisting that can be considered a spring, rotational spring, because it resists the motion, the rotation of this part. So we will still have spring here. So if we have now instead of a force, I apply a torque at that direction, tau. Then instead of x as my output or displacement, this will be theta displacement. And I will still call this one key, yes. So that tau now, the tau due to the spring is just equal to, if my output is the angular displacement, then this is just equal the same as ks times that theta. These are all in time domain. But if my output is in angular velocity instead of angular displacement, then the torque due to the spring will be equal to, it's just equal to because this is uh, velocity, angular velocity, omega is equal to theta dot. If you take the integral of that, you can get theta, and theta will be equal to the integral of that omega dt dt from 0 to t. So this is if your output is the angular velocity. Torque, angular velocity. You use this one if it's torque, input torque, output angular displacement. And also for the acceleration, if you want the acceleration, just like what we did in the translational system. And we also have dampers for rotational system, because if we rotate something inside a the same shape, Then there's also a friction when you are rotating. Example of this is the bearing. If you put something in a bearing, then you rotate it, then there's a friction, a slight friction in that, and we can model that using a damper. But again, we will be rotating this with torque, then the angular displacement theta, and this is kd. Then that torque due to the damper tau d. This is in time domain. If my output is the angular displacement, then this will be equal to, because it's proportional to the velocity, this should be kd times the velocity, which is the first derivative of the angular displacement. So if I want the angular velocity instead of displacement, then this is just kd times theta t. So this is for omega t. So this is for what? This is for torque and angular displacement. Angular displacement. And this one is for torque, angular velocity. Then for the mass, instead of mass, we have the inertia. So if we have an inertia here, if I rotate this, torque, I've applied torque, then this is also my displacement. If this is g, the inertia of this mass, then the force that resists that torque due to that one will be, this is just equal to the, it's like in translational, mass times the acceleration. So here it will be mass times the also acceleration, but angular acceleration alpha, or this is g times omega dot, or this is g times double dot, the second derivative of the angular displacement. So these are the different parameters. Now let's try to apply them with an example. So if we have a elongated round bar, so if this is our bar, then we have at this part a bearing. So this is a bearing. We also have a bearing at this part. Then I rotate this. I have an input. I apply a torque tau. So that will be my input. Then if I rotate it, my output will be, this will also rotate. We have an angular displacement here. Let's name it theta 1, because we have also another displacement here. They will not rotate at the same time because there's a spring. It's like a spring between them. So we can divide it into two inertias, theta 2. So the problem is, I want to determine the transfer function. If my input is tau, input is a torque, I apply a torque, then my output is theta 2, the angular displacement. So if we have a damping here, two dampers, let's call them the damping coefficients KD1 and KD2. So if we draw the symbol, this will be, we can divide it into into inertias. And between them will be a spring, because we will rotate that part, and the other terminal will not rotate immediately here. Then we have a damper at both sides of the rounder. Then we have also damper here. Then this will be J1 and this will be J2. And here we will apply our torque tau, and we have a angular displacement, and also at this part we have an angular displacement theta 2. So it will be KD1, and this is also KD2, and the spring has a spring constant Ks. Determine the transfer function when output is theta 2 and input is torque tau. So to do this, we draw the free body diagram first at G1. At G1, let's draw the free body diagram at G1. So if this is G1, then we apply our input torque in that direction. Then the displacement will be also in this direction, theta 1. Then what are the torque that are also in G1? We have the torque due to the damping. So tau, let's call it D1, due to KD1. And also due to spring, tau S. But this tau S, this spring, it's connected between J1 and J2. So if we want to solve for the total or the torque now, it will be the difference between theta 1 minus theta 2 times that spring constant. So if we take the summation of torques, should be equal to J1 squared, just like in, or J1. This is just J1 multiplied mass times the acceleration, because our output is theta. So let's just use theta double dot t. So it's the acceleration, angular acceleration. So what are the torques we have? First, we have the torque, the input torque. Then we have counterclockwise positive, or clockwise positive, then counterclockwise negative. So we have minus tau due to the damping, and tau due to spring. And this should be equal to J1 double dot t. This is our input. It's fine. Our torque due to KD1, we already know this one here. It's just equal to KD times, because this is D1, so KD1 times the first derivative of the angular displacement. Then this should be minus due to spring. And the one due to spring is, we have Ks, and we need to multiply it with the difference between the angular displacement of G at G1 and at G2. So this is theta 1. By the way, this is also theta 1. This is also theta 1, because we are taking our free body diagram at J1. But for the spring, because it's connected to J2, so we need to subtract the angular displacement at J2, theta 2. And this is J1. So this is our differential equation at J1. Now, we can now apply the Laplace to determine the S domain equivalent of this. So this tau here now will become capital T in S domain. This is now in S domain. This is in time domain. These are all time domain before. But now we are applying Laplace transform. So they will become, we transform into the S domain. So we have T minus, this is the first derivative. So it should be KD1 times S. Then it will be, this will be capital theta in S domain. Then this is two parts here. We have Ks times this one. So this is just minus Ks times theta 1 in S domain minus theta 2 in S domain. And this is equal to J1. This is a second order, so S squared. Then theta, this is 1, theta 1 in S domain. Then we can rearrange this into the form, we can factor out theta 1s, and we can solve for the input. Then all the rest, we put it at the other side. This will be equal to, then factor out that theta 1s. So we have J1s squared. Then we have this one, KDS. It will be put at the right side, so it will become positive, KD1 times S. Then for this one, theta 1s minus Ks, so plus Ks. multiplied by theta 1 s. Then we have still minus k minus theta 2. So this will become minus ks theta 2 s. So we have theta 1s and we have theta 2s. So we cannot still solve for the transfer function because we have three variables here. We have theta 2 and theta 1. We don't want theta 1. We need theta 2 and t because that's our output and input. So we need to find a way to solve for theta 1 by using the other inertia, J2. So at J2, we apply again J2, our free body diagram. What are the torques that are in this inertia? This, if that is the direction of the angular displacement, theta 2. So what are the torques here? We have a damping at that side. So it opposes that motion. This will be tau due to the damping D2. Then we still have due to the spring, tau S. At this time, our tau S, instead of theta 1 minus theta 2, because we are in J2, so it should be theta 2 minus theta 1. Then we apply again the summation of tau, and this should be equal to J2. And this time, instead of theta 1, this is now theta 2, double dot, and J2. So what are the taus? We have negative due to dumping minus tau S equals J2 theta 2 dot, double dot. Then what is tau D2? So this should be negative times, we multiply it with the constant KD2 and we multiply it with the velocity or theta dot, first derivative, because this is 2, so this should be theta 2 t. Then for theta S, or for tau S, Ks, we multiply it with theta 2 now minus theta 1 equals J2 theta 2 double dot. Then we take the Laplace of this, so we have negative KD2. Then first derivative, so multiply it by S. Then we make it capital theta in S domain. Minus, we have Ks, we multiply it with theta 2 minus theta 1. Then this should be equal to J2. You multiply it with S squared because this is second derivative, and theta S. And just like what we did here, we need to rearrange this and solve for theta 1. We need to remove that theta 1 in our equation. We need to make it just theta 2 and Ts, T of S, the input and the output. So we need to solve theta 1 from this equation. So where is our theta 1? Should be theta 2 here. This is our theta 1, and this should be theta 2. So we have, if we distribute this and put all the other at the other side, so we have negative, negative, positive, Ks times theta 1, theta 1 S, and they are all equal to J2 S squared. And we can also factor out that theta 2. Then we have minus KD2 S times theta 2. It will become positive. KD2 times S. We factor out that theta 2. Then lastly, for negative Ks times theta 2. So this will become positive Ks. And all of them multiplied by theta 2. Then, so theta S now, divide both sides by Ks of S. So theta 1 S now will be equal to J2 S squared plus KD2 S plus Ks all over Ks of S times theta 2 S. Then we will substitute this one to our first equation here, so that the remaining variables here will be just t and theta 2. Copy. Then I'll substitute this one here, replace the theta 1 with that. So we have, I'll just copy this. is 1 multiplied by theta 1s. Our theta 1s is this. Copy, then paste. So this is our theta 1s. This is ks. Then we subtract ks theta 2s. So if you look at the equation now, we only have t and theta 2 because that is what we want. We want output over input. So we rearrange again this to solve for our transfer function. So we can multiply these two. We can add them. So then we can factor out tau, theta 2s. T of s will be equal to multiply this one, j1 s squared plus kd1 times s plus k of s. You multiply it with j2 s squared plus kd2 times s plus ks. We divide it with ks, then we subtract k of s. And we multiply this with theta 2 of s. Then output over input, our output is theta 2s. But before that, we can simplify this further. Theta s, we can add ks, then just copy this numerator. Then ks divided by 1. Ks divided by 1 times ks, so minus ks squared. Then theta 2 of s. So the transfer function now, g of s, which is theta 2 divided by t, will be equal to, if we just inverse this, it will be equal to k of s all over this 1. This is k of s. So this is now the transfer function of that rotational system. Okay?